Space, the final frontier, the infinite canvas upon which every star, every galaxy, and every mystery of existence is painted. Tonight we embark on an extraordinary journey, a journey that will take us from the blazing surface of our own sun to the farthest edges of the observable universe. What you are about to hear will challenge everything you thought you knew about the cosmos. Some of these revelations will leave you breathless. Others will make you question the very nature of reality itself. This is the story of space, raw, unfiltered, and absolutely magnificent. Please let us know in the comments where you are watching this documentary and what time you are watching it, and be sure to subscribe to the channel for future videos. Let us begin where all things begin, with the sun. That brilliant sphere of light that rises every morning, warming our skin, feeding our crops, sustaining every living organism on this planet. We take it for granted. We glance at it through squinted eyes and move on with our day, but if you truly understood what the sun is, you would never look at it the same way again. The sun is a star. That might sound obvious, but pause and consider what that really means. Every tiny point of light you see in the night sky is a sun, many of them far larger, far hotter, and far more luminous than ours. Our sun is classified as a G-type main sequence star, sometimes called a yellow dwarf. It has been burning for approximately 4.5 billion years, and it has enough hydrogen fuel left in its core to continue burning for another 5 billion years. That is an almost incomprehensible span of time. Civilizations will rise and fall, species will evolve and go extinct, continents will drift and collide, and through all of it the sun will continue to burn. But here is the part that truly staggers the imagination. Every single second, the sun converts roughly 600 million tons of hydrogen into helium through a process called nuclear fusion. In doing so, it loses about 4 million tons of mass, not into waste, not into debris, but into pure energy. That energy radiates outward in all directions as light, heat, and other forms of electromagnetic radiation. The light that reaches your eyes right now left the surface of the sun about 8 minutes and 20 seconds ago. That means when you watch a sunset, you are not seeing the sun where it is. You are seeing where it was over 8 minutes in the past. In a very real sense, you are always looking back in time when you look at the sun. And yet, for all its power, the sun is remarkably average. In the grand catalog of stars that populate our galaxy, the sun is neither particularly large nor particularly small. It is not especially hot, and it is not unusually cool. It sits comfortably in the middle of the stellar spectrum, which is, in many ways, exactly what makes it so perfect for supporting life on Earth. A star much larger would burn through its fuel too quickly, not giving life enough time to evolve. A star much smaller might not provide enough warmth to sustain liquid water on a planet's surface. Our sun is, in the language of astrophysics, just right. But let us talk about what happens inside that star, because the interior of the sun is one of the most extreme environments in the known universe. At its core, the temperature reaches approximately 27 million degrees Fahrenheit. The pressure is so intense, roughly 340 billion times the atmospheric pressure at sea level on Earth, that hydrogen atoms are forced together, their nuclei merging to form helium. This is the same process that powers a thermonuclear weapon, except the sun does it continuously, every second of every day, and has been doing so for billions of years. The energy produced in the core takes an astonishingly long time to reach the surface. A single photon of light generated in the sun's core may take anywhere from 10,000 to 170,000 years to make its way to the surface, bouncing and being absorbed and ray-emitted countless times along the way. But once it reaches the surface and escapes into space, it travels at the speed of light and reaches Earth in just over 8 minutes. Think about that. The light warming your face today began its journey inside the sun tens of thousands of years ago, long before the first cities were built, long before the first words were written. Now, let us leave the sun behind and move outward into the realm of the planets. Our solar system is a place of extraordinary diversity, and each world within it tells a different story about the forces that shaped our cosmic neighborhood. Mercury, the closest planet to the sun, is a world of extremes. During the day, its surface temperature can soar to around 800 degrees Fahrenheit. At night, it plummets to nearly -300 degrees. This dramatic swing occurs because Mercury has virtually no atmosphere to trap heat or distribute warmth. It is a barren, cratered world bearing the scars of billions of years of meteorite impacts. And despite being the closest planet to the Sun, Mercury is not the hottest planet in our solar system. That distinction belongs to Venus. Venus is often called Earth's twin because the two planets are similar in size, mass, and composition. But that is where the similarities end. Venus is a nightmare world. Its thick atmosphere is composed almost entirely of carbon dioxide, with clouds of sulfuric acid drifting through its skies. This dense atmosphere creates a runaway greenhouse effect so intense that the surface temperature of Venus averages around 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure on the surface is roughly 90 times that of Earth, equivalent to being nearly a mile beneath the ocean's surface. If you were to stand on Venus without protection, you would be simultaneously crushed, suffocated, dissolved by acid, and incinerated. No spacecraft that has ever landed on Venus has survived for more than a couple of hours, and yet there is something hauntingly beautiful about Venus. It is the brightest natural object in the night sky after the moon, and it has been admired by civilizations throughout history. Ancient observers called it the morning star and the evening star, not realizing that both appearances were the same planet. Venus rotates on its axis in the opposite direction from most other planets, meaning the sun rises in the west and sets in the east. And a single day on Venus, one complete rotation, takes longer than a Venusian year. Venus orbits the sun in about 225 Earth days, but it takes 243 Earth days to complete one rotation. So on Venus, a day is longer than a year. Let that sink in for a moment. Moving outward, we come to Earth, our home. But we will not linger here because the purpose of this journey is to explore what lies beyond the familiar. So let us press on to Mars, the red planet which has captured human imagination for centuries. Mars gets its distinctive red color from iron oxide rust that covers much of its surface. It is a cold, dry, dusty world with a thin atmosphere composed mostly of carbon dioxide. The average temperature on Mars is about -80 degrees Fahrenheit, though it can vary significantly depending on the season and location. Mars has the largest volcano in the solar system, Olympus Mons, which stands nearly 72,000 feet tall, almost 2.5 times the height of Mount Everest. It is so wide at its base that if you stood on the rim, you would not be able to see the edges because they would extend beyond the curvature of the planet. Mars also hosts the largest canyon system in the solar system, Valles Marineris, which stretches over 2,500 miles across the Martian surface. To put that in perspective, it is roughly the distance from the east coast to the west coast of a large continent. If Valles Marineris were on Earth, it would stretch across an entire landmass. The canyon is up to 4.5 miles deep in some places, making it nearly 4 times deeper than the Grand Canyon. But perhaps the most tantalizing aspect of Mars is the evidence that it once had liquid water on its surface. Orbital photographs have revealed ancient riverbeds, lake basins, and mineral deposits that only form in the presence of water. There is strong evidence that billions of years ago, Mars had a thicker atmosphere and warmer temperatures, conditions that could have supported liquid water and potentially microbial life. Whether life ever actually existed on Mars is one of the most profound unanswered questions in science. The search continues, with rovers and orbiters studying the planet's surface and subsurface for any signs of past or present biological activity. Now let us venture further out past the asteroid belt, that ring of rocky debris that separates the inner planets from the outer planets, and enter the domain of the gas giants, beginning with Jupiter. Jupiter is the king of the planets. It is the largest planet in our solar system by a tremendous margin. You could fit more than 1,300 Earths inside Jupiter and still have room to spare. Its mass is more than twice that of all the other planets in the solar system combined. Jupiter is not a solid world like Earth or Mars. It is composed primarily of hydrogen and helium, with no well-defined solid surface. If you tried to land on Jupiter, you would simply sink deeper and deeper into increasingly dense layers of gas until the pressure became so great that the hydrogen transitioned into a liquid and eventually into a metallic state. Jupiter's most famous feature is the Great Red Spot, a massive storm system that has been raging for at least 350 years and possibly much longer. The Great Red Spot is so large that 2 or 3 Earths could fit inside it. Wind speeds within the storm can exceed 400 miles per hour. Despite centuries of observation, scientists are still not entirely sure what gives the Great Red Spot its distinctive color. The leading theories involve complex chemical reactions between compounds in Jupiter's atmosphere and ultraviolet radiation from the Sun. Jupiter also has a powerful magnetic field, roughly 20,000 times stronger than Earth's. This magnetic field creates intense radiation belts around the planet that would be lethal to unprotected humans. The Juno spacecraft, which has been orbiting Jupiter since 2016, carries specially designed radiation shielding to protect its sensitive electronics from this harsh environment. And then there are Jupiter's moons. Jupiter has at least 95 known moons, and the 4 largest, Io, Europa, Ganymede, and Callisto, were first observed by Galileo Galilei in 1610. These 4 moons, known as the Galilean moons, are worlds unto themselves. Io is the most volcanically active body in the solar system. Its surface is covered with hundreds of volcanoes, some of which send plumes of sulfur and sulfur dioxide hundreds of miles into space. This intense volcanic activity is driven by tidal heating. The gravitational tug-of-war between Jupiter and the other large moons literally squeezes and stretches Io's interior, generating enormous amounts of heat. Europa, on the other hand, is covered in a shell of ice. Beneath that ice, scientists believe there exists a vast ocean of liquid water, an ocean that may contain more water than all the oceans on Earth combined. The presence of liquid water, combined with the energy provided by tidal heating and the chemical compounds present on Europa's surface, makes it one of the most promising places in the solar system to search for extraterrestrial life. Future missions are being planned to study Europa's ice shell and eventually to drill through it and explore the ocean beneath. Ganymede is the largest moon in the solar system, larger even than the planet Mercury. It is the only moon known to have its own magnetic field, a fact that has puzzled scientists for decades. Callisto, the outermost of the 4 Galilean moons, is one of the most heavily cratered objects in the solar system, suggesting that its surface is ancient and has experienced very little geological activity. Beyond Jupiter lies Saturn, the jeweled planet famous for its spectacular ring system. Saturn's rings are one of the most visually stunning features in the entire solar system, and they have fascinated astronomers since Galileo first observed them through his telescope in 1610, though he did not recognize them as rings. He described them as ears or handles on either side of the planet. Saturn's rings are composed primarily of particles of water ice, ranging in size from tiny grains to chunks as large as houses. Despite their impressive appearance, the rings are remarkably thin. In most places, they are only about 30 feet thick. If you were to shrink Saturn's rings down to the diameter of a standard football field, they would be thinner than a razor blade. The origin of Saturn's rings is still debated. One popular theory suggests they formed from the breakup of a moon or comet that ventured too close to Saturn and was torn apart by tidal forces. Recent data from the Cassini spacecraft suggests that the rings may be relatively young, perhaps only 100 to 200 million years old, which means they may not have existed during the age of the dinosaurs. Saturn itself is a gas giant like Jupiter, composed mostly of hydrogen and helium. It is the least dense planet in the solar system, so light, in fact, that if you could find a bathtub large enough, Saturn would float. Its density is about 70% that of water. Saturn also has the fastest winds in the solar system, with speeds near its equator reaching up to 1,100 miles per hour. Like Jupiter, Saturn has a large family of moons. The most intriguing of these is Titan, Saturn's largest moon. Titan is the only moon in the solar system with a substantial atmosphere thicker, in fact, than Earth's. Its atmosphere is composed primarily of nitrogen, with methane and ethane playing roles similar to water on Earth. Titan has lakes and seas on its surface, but they are filled not with water, but with liquid methane and ethane. It rains methane on Titan. Rivers of liquid methane carve channels through the icy landscape and flow into vast hydrocarbon seas. The Huygens probe, which landed on Titan's surface in 2005, sent back images of a world that looked eerily similar to Earth, with shorelines, riverbeds, and smooth pebbles rounded by flowing liquid. Except everything was made of ice and hydrocarbons instead of rock and water. Another of Saturn's moons, Enceladus, has also captured scientific attention. This small, icy moon has geysers near its south pole that shoot plumes of water vapor and ice particles into space. These plumes originate from a subsurface ocean of liquid water, and they contain organic molecules and molecular hydrogen, potential indicators of hydrothermal activity on the ocean floor. Like Europa, Enceladus is considered a prime candidate in the search for life beyond Earth. Let us continue our outward journey to Uranus, the tilted planet. Uranus is unique among the planets because it rotates on its side. Its axial tilt is approximately 98 degrees, meaning it essentially rolls around the sun like a ball rather than spinning like a top. This extreme tilt is thought to be the result of a massive collision with an Earth-sized object early in the solar system's history. Because of this tilt, Uranus experiences extreme seasons. Each pole gets around 42 years of continuous sunlight followed by 42 years of continuous darkness. Uranus is classified as an ice giant, a distinction it shares with Neptune. Unlike the gas giants Jupiter and Saturn, which are composed primarily of hydrogen and helium, ice giants contain significant amounts of heavier elements, including water, methane, and ammonia. It is the methane in Uranus's atmosphere that gives the planet its distinctive pale blue-green color. Methane absorbs red light from the sun and reflects blue and green light back into space. Uranus is also bitterly cold. Its atmosphere is the coldest of any planet in the solar system, with temperatures dropping to around -370 degrees Fahrenheit. Scientists are not entirely sure why Uranus is so cold. Unlike the other giant planets, it seems to emit very little internal heat, which suggests something unusual about its internal structure and thermal history. Neptune, the eighth and outermost planet, is a world of superlatives. It has the strongest sustained winds of any planet in the solar system, with gusts reaching up to 1,500 miles per hour. It is a deep, vivid blue, a color caused, like Uranus, by methane in its atmosphere, though Neptune's blue is far more intense, suggesting that some additional unknown atmospheric component contributes to its striking hue. Neptune was the first planet to be discovered through mathematical prediction rather than direct observation. In the 1840s, mathematicians independently calculated that the gravitational pull of an unseen planet was affecting the orbit of Uranus. When astronomers pointed their telescopes at the predicted location, there was Neptune, right where the mathematics said it would be. This was a triumph of human intellect, using nothing but pen, paper, and the laws of physics to discover a new world. Neptune's largest moon, Triton, is one of the coldest objects in the solar system, with surface temperatures around -390 degrees Fahrenheit. Triton orbits Neptune in a retrograde direction, opposite to the planet's rotation, which strongly suggests that Triton is not a native moon of Neptune, but was captured from the Kuiper Belt, a vast region of icy bodies beyond Neptune's orbit. Triton has active geysers that erupt nitrogen gas and dark particles into its thin atmosphere, creating dark streaks on its frozen surface. Beyond Neptune lies the Kuiper Belt, a donut-shaped region of icy bodies that extends from Neptune's orbit outward to roughly 50 times Earth's distance from the Sun. The most famous resident of the Kuiper Belt is Pluto, which was considered the ninth planet for 76 years before being reclassified as a dwarf planet in 2006. This reclassification sparked considerable controversy and public debate, but it was driven by a growing understanding that Pluto is just one of many similar objects in the Kuiper Belt, and not even the largest one. Eris, another Kuiper Belt object discovered in 2005, is actually more massive than Pluto, though slightly smaller in diameter. The New Horizons spacecraft flew past Pluto in July 2015, giving us our first close-up look at this distant world. What it revealed was nothing short of astonishing. Pluto is far more geologically complex than anyone had expected. Its surface features a vast, heart-shaped plain of nitrogen ice called Sputnik Planitia, towering mountains of water ice, and evidence of recent geological activity. The fact that a small, cold world so far from the sun could be so dynamic challenged many assumptions about planetary science. Now let us shift our focus from the planets and moons of our solar system to something far larger and far more mysterious, the structure of the universe itself. When you look up at the night sky, you see stars, thousands of them if you are far from city lights. But what you are seeing is only a tiny fraction of the stars in our galaxy, the Milky Way. The Milky Way contains an estimated 100 billion to 400 billion stars. That number is so large that it defies comprehension. If you tried to count every star in the Milky Way at a rate of 1 star per second, it would take you over 3,000 years to finish without sleeping, eating, or taking a single break. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years in diameter. A light-year is the distance that light travels in 1 year, approximately 5.88 trillion miles. So the Milky Way is roughly 588 quadrillion miles across. Our solar system is located about 26,000 light-years from the galactic center, in one of the spiral arms known as the Orion Arm. We orbit the center of the galaxy at a speed of roughly 515,000 miles per hour, and even at that tremendous speed, it takes our solar system about 230 million years to complete one orbit. The last time Earth was in this same position relative to the galactic center, dinosaurs had not yet appeared on our planet. At the very center of the Milky Way lurks something extraordinary, a supermassive black hole known as Sagittarius A star. This black hole has a mass equivalent to roughly 4 million suns, compressed into a region of space smaller than our solar system. Despite its enormous mass, Sagittarius A star is invisible to the naked eye, hidden behind vast clouds of gas and dust. It was detected through its gravitational influence on nearby stars, which orbit the galactic center at tremendous speeds. In 2022, the Event Horizon Telescope collaboration released the first-ever image of Sagittarius A star, revealing the shadow of the black hole surrounded by a glowing ring of superheated gas. This was a landmark achievement in observational astronomy. But what exactly is a black hole? To understand that, we need to talk about gravity and the life cycle of stars. Stars are born in vast clouds of gas and dust called nebulae. Within these clouds, gravity causes regions of higher density to collapse inward, drawing more and more material together. As the collapsing material heats up, it eventually reaches temperatures and pressures sufficient to ignite nuclear fusion in the core, and a new star is born. The star then enters a long, stable period of its life known as the main sequence, during which it fuses hydrogen into helium in its core, producing the energy that makes it shine. How a star lives and dies depends primarily on its mass. Stars like our Sun will burn steadily for about 10 billion years. As they exhaust their hydrogen fuel, they expand dramatically, becoming red giants. Our Sun, when it reaches this stage in about 5 billion years, will swell to such an enormous size that it will engulf the orbits of Mercury and Venus, and possibly Earth as well. After the red giant phase, the outer layers of the star are gently expelled into space, forming a beautiful structure called a planetary nebula. The remaining core collapses into a dense, compact object called a white dwarf, roughly the size of Earth but with a mass comparable to the Sun. A teaspoon of white dwarf material would weigh about 15 tons on Earth. Over billions of years, white dwarfs gradually cool and fade, eventually becoming cold, dark objects known as black dwarfs. However, the universe is not yet old enough for any white dwarfs to have cooled completely, so black dwarfs remain theoretical. But for stars significantly more massive than the Sun, stars with at least 8 to 10 times our Sun's mass, the ending is far more dramatic. These massive stars burn through their fuel much more quickly, living fast and dying young in cosmic terms. When a massive star exhausts its fuel, it can no longer support itself against the crushing force of its own gravity. The core collapses in a fraction of a second, and the outer layers of the star are blasted outward in a cataclysmic explosion known as a supernova. A supernova is one of the most violent events in the universe. For a brief period, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. The energy released in a supernova is almost beyond comprehension, more energy in a few seconds than the Sun will produce in its entire 10 billion-year lifetime. Supernovae are not merely destructive, however. They are also profoundly creative. The extreme temperatures and pressures generated during a supernova are responsible for forging many of the heavy elements that make up the world around us, elements like gold, silver, platinum, and uranium. These elements are blasted into space by the explosion, where they mix with interstellar gas and dust, eventually becoming part of new stars, new planets, and new life. Every atom of gold in every ring, every necklace, every bar in every vault was created in the heart of an exploding star billions of years ago. You are quite literally made of stardust. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the nuclear furnaces of ancient stars that died long before our Sun was born. After a supernova, the fate of the core depends on its remaining mass. If the core has a mass between about 1.5 and 3 times the mass of the Sun, it collapses into a neutron star, one of the most exotic objects in the universe. A neutron star is incredibly dense. A typical neutron star is only about 12 miles in diameter, roughly the size of a city, but it contains more mass than the entire Sun. A single teaspoon of neutron star material would weigh about 6 billion tons. The gravitational field on the surface of a neutron star is so intense that if you dropped an object from a height of 1 meter, it would hit the surface traveling at about 4.5 million miles per hour. Some neutron stars rotate at astonishing speeds, spinning hundreds of times per second. These rapidly rotating neutron stars emit beams of electromagnetic radiation from their magnetic poles, and if one of those beams happens to sweep across Earth, we detect it as a regular pulse of radio waves. These pulsing neutron stars are called pulsars, and when they were first discovered in 1967, their signals were so regular that astronomers briefly entertained the possibility that they might be signals from an extraterrestrial civilization. They even jokingly labeled the first pulsar signal LGM-1, standing for Little Green Men. If the core remaining after a supernova has a mass greater than about 3 times the mass of the Sun, not even the immense pressure of neutrons packed together can halt the collapse. The core continues to shrink, crushing itself into a single point of infinite density called a singularity. The gravitational pull around this singularity becomes so strong that nothing, not even light, can escape. This is a black hole. The boundary around a black hole beyond which nothing can return is called the event horizon. It is not a physical surface. It is a mathematical boundary, a point of no return. If you were falling into a black hole, you would not necessarily notice anything special as you crossed the event horizon. But from that moment on, every possible path through space and time would lead inexorably toward the singularity at the center. There would be no escape, no turning back, no signal you could send to the outside universe. Black holes come in different sizes. Stellar mass black holes formed from the collapse of massive stars typically have masses between about 5 and several tens of times the mass of the Sun. Supermassive black holes like Sagittarius A star at the center of our galaxy have masses ranging from millions to billions of times the mass of the Sun. How supermassive black holes form is still not fully understood. They may grow over time by accreting matter and merging with other black holes, but some supermassive black holes appear to have existed when the universe was very young, which poses a challenge for current models of black hole growth. There are also intermediate mass black holes, with masses between about 100 and 100,000 times the mass of the Sun. These have been much harder to detect, but recent observations have provided growing evidence for their existence. And at the other end of the scale, theoretical physicists have speculated about the existence of primordial black holes, tiny black holes that may have formed in the extreme conditions of the early universe, fractions of a second after the Big Bang. Some of these primordial black holes, if they exist, could be smaller than an atom yet more massive than a mountain. Speaking of the Big Bang, let us turn our attention to the origin of the universe itself. This is, in many ways, the grandest story ever told. Approximately 13.8 billion years ago, the universe began, not in a particular place in space because space itself did not exist before the Big Bang, not at a particular moment in time because time itself began with the Big Bang. Everything, all matter, all energy, all space, and all time emerged from an unimaginably hot, dense state and has been expanding ever since. In the first fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion called inflation. During this brief epoch, the universe expanded by a factor of at least 10 to the 26th power, a 1 followed by 26 zeros, in less than a trillionth of a trillionth of a trillionth of a second. This inflationary period smoothed out the universe, making it remarkably uniform on the largest scales, and planted the seeds for the structures, galaxies, clusters of galaxies, and vast cosmic filaments that would later form under the influence of gravity. As the universe expanded and cooled, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, separated from what may have been a single unified force. Subatomic particles formed. Quarks combined to form protons and neutrons. Within the first few minutes, the universe had cooled enough for nuclear fusion to occur, and the first atomic nuclei were created, mostly hydrogen, with some helium and trace amounts of lithium. This process is called Big Bang nucleosynthesis, and the predicted abundances of these light elements match observations with remarkable precision, providing one of the strongest pieces of evidence for the Big Bang theory. For the next 380,000 years, the universe was a hot, dense plasma of particles and radiation, opaque to light. Photons could not travel far before being scattered by free electrons. But as the universe continued to expand and cool, it eventually reached a temperature at which electrons could combine with atomic nuclei to form neutral atoms. This event, known as recombination, made the universe transparent for the first time. The photons that were released at that moment have been traveling through space ever since, and we can still detect them today as the cosmic microwave background radiation, a faint glow of microwave light that fills the entire sky. The cosmic microwave background is, in a very real sense, the afterglow of the Big Bang, and its discovery in 1965 by Arno Penzias and Robert Wilson provided conclusive evidence that the Big Bang had actually occurred. After recombination, the universe entered a period known as the Cosmic Dark Ages, a time before any stars had formed, when the universe was filled with neutral hydrogen gas and nothing was producing visible light. This dark period lasted for roughly 100 to 200 million years, until gravity began to pull the densest regions of gas together, forming the first stars. These first stars were unlike any stars that exist today. They were enormous, perhaps hundreds of times the mass of our Sun, and they burned extremely hot and bright. They were composed entirely of hydrogen and helium, the only elements that existed at the time. Because they contain no heavier elements, they are called population II stars. None of these first stars survive today. They burned through their fuel quickly and exploded as supernovae, seeding the universe with the first heavy elements and paving the way for subsequent generations of stars like our Sun, which contain small but crucial amounts of these heavier elements. The first galaxies began to form within the first billion years of the universe's history. These early galaxies were small and irregular, gradually growing larger through mergers and the accretion of gas. Over billions of years, these mergers built up the grand spiral and elliptical galaxies we see today. The Milky Way itself has consumed numerous smaller galaxies over its history, and it continues to do so. The Sagittarius dwarf elliptical galaxy is currently being torn apart and absorbed by the Milky Way's gravitational pull. And in the distant future, the Milky Way will undergo its most dramatic merger yet. Our galaxy is on a collision course with the Andromeda Galaxy, the nearest large galaxy to us, located about 2.5 million light-years away. The two galaxies are approaching each other at roughly 250,000 miles per hour and are expected to collide in about 4 to 5 billion years. When they do, the two galaxies will merge over the course of several billion years, eventually forming a single, larger galaxy that astronomers have nicknamed Milkomeda. Despite the dramatic nature of this event, individual stars are so widely spaced that actual stellar collisions would be extremely rare. Our solar system, if it still exists at that point, would likely survive the merger, though it might be flung to a very different location within the new combined galaxy. Now let us talk about something that constitutes the vast majority of the universe, yet remains one of the deepest mysteries in all of science: dark matter and dark energy. When astronomers observe the motion of stars within galaxies and the motion of galaxies within clusters, they consistently find that these objects are moving faster than they should be based on the amount of visible matter present. The gravitational pull of the stars, gas, and dust that we can see is simply not strong enough to account for the observed motions. Something else must be providing additional gravitational pull, something invisible. This invisible substance is called dark matter. Dark matter does not emit, absorb, or reflect light. It does not interact with electromagnetic radiation in any detectable way. It can only be inferred through its gravitational effects on visible matter and on the large-scale structure of the universe. And there is a lot of it. Current estimates suggest that dark matter makes up about 27% of the total mass energy content of the universe. Ordinary matter, the atoms that make up stars, planets, and people, accounts for only about 5%. That means everything you have ever seen, touched, or measured constitutes less than 1/20th of what the universe is actually made of. Scientists have proposed various candidates for dark matter, including weakly interacting massive particles, or WIMPs, and axions, hypothetical particles that interact with normal matter only through gravity and possibly the weak nuclear force. Despite decades of searching, no dark matter particle has been directly detected. Enormous underground detectors, particle accelerators, and space-based telescopes have all been employed in the hunt, but dark matter remains stubbornly elusive. It is one of the most important unsolved problems in modern physics. And then there is dark energy, which is even more mysterious. In 1998, two independent teams of astronomers made a stunning discovery while studying distant supernovae. They found that the expansion of the universe is not slowing down, as most scientists had expected. Instead, it is speeding up. The expansion of the universe is accelerating, driven by some unknown force that acts in opposition to gravity, pushing galaxies apart at an ever-increasing rate. This mysterious force was named dark energy. Dark energy is estimated to make up about 68% of the total mass energy content of the universe. Combined with dark matter's 27%, this means that 95% of the universe is composed of stuff we cannot see, cannot touch, and do not understand. Only 5% of the universe is made of ordinary matter, the stuff of stars, planets, trees, and human beings. We are, in the most literal sense, a tiny minority in our own universe. The nature of dark energy is completely unknown. Some physicists have suggested it might be a property of space itself, that empty space has its own intrinsic energy that causes it to expand. Others have proposed that dark energy might be related to a new, undiscovered field that permeates the universe. Still others have suggested that our understanding of gravity might be incomplete, and that the observed acceleration could be explained by modifications to Einstein's general theory of relativity. At this point, we simply do not know, and the quest to understand dark energy is one of the most active and important areas of research in cosmology. Let us now turn to one of the most mind-bending consequences of Einstein's theories, the nature of space and time themselves. In 1905, Albert Einstein published his special theory of relativity, which fundamentally changed our understanding of space and time. One of the key insights of special relativity is that space and time are not separate, independent entities. They are woven together into a single four-dimensional fabric called spacetime. Events do not simply happen at a place in space and at a moment in time, they happen at a point in spacetime. Another consequence of special relativity is that the speed of light in a vacuum, approximately 186,000 miles per second, is the ultimate speed limit of the universe. Nothing with mass can reach the speed of light. As an object with mass moves faster, its energy increases and it becomes harder and harder to accelerate further. To accelerate a massive object to the speed of light would require an infinite amount of energy, which is physically impossible. But perhaps the most counterintuitive prediction of special relativity is time dilation. According to Einstein, time does not pass at the same rate for all observers. The faster you move through space, the slower time passes for you relative to a stationary observer. This is not a theoretical abstraction, it is a measurable physical reality. Atomic clocks placed on high-speed aircraft have been shown to tick slightly slower than identical clocks on the ground, exactly as Einstein's equations predict. The Global Positioning System satellites, which orbit Earth at high speeds and in weaker gravitational fields, must account for relativistic time dilation in their calculations. Without these corrections, GPS positions would drift by several miles per day. If you could somehow travel at 99% of the speed of light, time would pass for you at roughly 1/7 the rate it passes for someone standing still. If you traveled for what felt like 1 year to you, about 7 years would have passed on Earth. At 99.9% of the speed of light, the ratio increases to about 22:1, and at 99.999%, you could travel for 1 year while over 700 years passed on Earth. This means that, in principle, fast enough travel could take you into the far future. Time travel to the future is not science fiction. It is a straightforward consequence of the physics we already know. In 1915, Einstein extended his theory to include gravity, producing the general theory of relativity. In this framework, gravity is not a force in the traditional sense. Instead, massive objects curve the fabric of spacetime around them, and other objects follow the curves in spacetime. Imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a dip in the sheet, and smaller balls placed nearby will roll toward it. This is, very roughly, how gravity works in general relativity. The Sun curves spacetime around it, and Earth follows the curves in spacetime, which we perceive as an orbit. General relativity also predicts that time passes more slowly in stronger gravitational fields. This is called gravitational time dilation. A clock at the top of a tall building runs ever so slightly faster than a clock at ground level, because the clock at the top is in a slightly weaker gravitational field. Near a black hole, where the gravitational field is enormously strong, time dilation becomes extreme. An observer watching someone fall toward a black hole would see them appear to slow down and freeze at the event horizon, never quite crossing it. From the perspective of the person falling in, however, they would cross the event horizon in finite time and continue falling toward the singularity. One of the most spectacular predictions of general relativity is the existence of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects. Einstein predicted gravitational waves in 1916, but he believed they would be too faint to ever detect. He was almost right. It took a century of technological development before gravitational waves were finally detected on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, known as LIGO. The waves that were detected had been produced by the merger of two black holes, each about 30 times the mass of the Sun, over 1 billion light-years away. The collision was so violent that it radiated more energy in a fraction of a second than all the stars in the observable universe combined. And yet, by the time the gravitational waves reached Earth, they had stretched and compressed the 4-kilometer arms of the LIGO detector by less than 1,000th the diameter of a proton. The detection of gravitational waves opened an entirely new window on the universe, allowing scientists to observe cosmic events that produce little or no light. Let us now journey to the farthest reaches of the observable universe and contemplate its sheer scale. The observable universe is the portion of the universe from which light has had time to reach us since the Big Bang. Because the universe is approximately 13.8 billion years old, you might expect the observable universe to have a radius of 13.8 billion light years. But because the universe has been expanding throughout its history, the most distant objects we can see are actually about 46.5 billion light years away. The observable universe, therefore, has a diameter of about 93 billion light years. Within this observable volume, there are an estimated 2 trillion galaxies. 2 trillion. Each of those galaxies contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is estimated to be around 200 billion trillion, a 2 followed by 23 zeros. That number is greater than the number of grains of sand on every beach on Earth. And yet, for all its stars and galaxies, the universe is overwhelmingly empty. The distances between stars, even within a single galaxy, are almost inconceivably vast. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. At the speed of our fastest spacecraft, it would take roughly 70,000 years to reach it. The distances between galaxies are even more staggering. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. The most distant galaxies observed are over 13 billion light-years away. Their light has been traveling since the universe was less than 1 billion years old. On the largest scales, the universe is organized into a vast cosmic web, a network of filaments and walls of galaxies separated by enormous empty voids. The filaments can stretch for hundreds of millions of light-years, and the voids between them can be hundreds of millions of light-years across and contain almost nothing. The largest known structure in the universe is the Hercules Corona Borealis Great Wall, a vast superstructure of galaxies roughly 10 billion light-years across. Its existence challenges some cosmological models, as it is difficult to explain how such a large structure could have formed in the time since the Big Bang. Let us now pause and consider something deeply profound, the fact that when we look out into the universe, we are looking back in time. Because light travels at a finite speed, the light from distant objects takes time to reach us. When you look at the moon, you see it as it was about 1.25 seconds ago. When you look at the sun, you see it as it was over 8 minutes ago. When you look at the nearest star, Proxima Centauri, you see it as it was over 4 years ago. The Andromeda Galaxy appears as it was 2.5 million years ago. And the most distant galaxies we can see appear as they were over 13 billion years ago, when the universe was young and the first stars were just beginning to shine. This means that telescopes are, in a very real sense, time machines. By looking at distant objects, we are observing the universe as it existed in the past. The farther we look, the further back in time we see. The cosmic microwave background, the oldest light in the universe, shows us the universe as it appeared just 380,000 years after the Big Bang, long before any stars or galaxies existed. By studying this ancient light, cosmologists can reconstruct the conditions of the early universe with remarkable precision. Now let us talk about something that bridges the realms of physics and philosophy, the search for extraterrestrial life. The question of whether we are alone in the universe is perhaps the most profound question humanity has ever asked. The sheer numbers involved in any calculation of cosmic demographics are staggering. There are an estimated 200 billion trillion stars in the observable universe. Recent discoveries have shown that planets are extremely common. Most stars have at least one planet orbiting them, and many have several. The Kepler Space Telescope, launched in 2009, discovered thousands of exoplanets and revealed that there are likely more planets than stars in our galaxy. Some of these planets orbit within their star's habitable zone, the range of distances at which liquid water could exist on a planet's surface, making them potential candidates for hosting life. Given these numbers, it seems almost inconceivable that Earth is the only planet in the entire universe where life has arisen. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, and other elements, are among the most abundant elements in the cosmos. Complex organic molecules have been detected in interstellar space, in the atmospheres of other planets, and in meteorites that have fallen to Earth. The building blocks of life appear to be everywhere. And yet, despite the seemingly favorable odds, we have not yet found any definitive evidence of life beyond Earth. This apparent contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the universe is teeming with potentially habitable worlds, and if life arises readily given the right conditions, then where are all the aliens? Why have we not detected their signals, their spacecraft, or their artifacts? Numerous explanations have been proposed for the Fermi paradox. Perhaps life is common, but intelligent life is extraordinarily rare. Perhaps civilizations tend to destroy themselves before they can develop the technology for interstellar communication or travel. Perhaps the distances between stars are simply too great, even for advanced civilizations. Perhaps intelligent aliens exist, but are deliberately avoiding contact with us. Perhaps the universe is teeming with microbial life, but bereft of complex organisms. Or perhaps, and this is the most unsettling possibility, we really are alone, a singular accident of chemistry and physics in an otherwise lifeless cosmos. The search for extraterrestrial intelligence, known as SETI, has been ongoing for decades. Radio telescopes around the world listen for signals that might indicate the presence of a technological civilization. So far, no confirmed signal has been detected, but the search continues with ever more powerful instruments and ever more sophisticated analysis techniques. In addition, new missions are being planned to study the atmospheres of exoplanets for biosignatures, chemical compounds, such as oxygen, methane, and ozone, that might indicate the presence of life. Let us shift gears now and talk about the remarkable history of human space exploration, the story of how we went from gazing at the stars in wonder to actually traveling among them. The modern era of space exploration began in October 1957, when the world's first artificial satellite was launched into orbit around Earth. This small, polished metal sphere, equipped with radio transmitters, circled the planet every 96 minutes, emitting a simple beeping signal that could be heard by anyone with a radio receiver. The launch stunned the world and ignited the space race, a fierce competition to achieve supremacy in spaceflight capability. The pace of progress was breathtaking. Within 4 years, a human being had orbited the Earth for the first time, completing a single orbit in April 1961. This flight lasted just 108 minutes, but it demonstrated that human beings could survive in space and return safely to Earth. It was a moment that changed history forever. The push to reach the moon became the defining challenge of the decade. It required the development of an enormous rocket, the most powerful ever built, standing taller than a 36-story building and generating 7.5 million pounds of thrust at liftoff. Hundreds of thousands of engineers, scientists, and technicians worked together on the project, solving problems that had never been encountered before. They had to figure out how to navigate in space, how to rendezvous and dock 2 spacecraft in orbit, how to land on an alien world, and how to bring astronauts home safely. On July 20th, 1969, 2 human beings set foot on the surface of the moon for the first time. The moment was watched by an estimated 600 million people around the world, the largest television audience in history up to that point. Over the course of 3 years, a total of 12 people walked on the moon, conducting experiments, collecting samples, and exploring the lunar surface. They brought back 842 pounds of moon rocks and soil, which continue to be studied by scientists to this day. the moon itself is a fascinating world. It is Earth's only natural satellite, roughly 1/4 the diameter of our planet. It is believed to have formed about 4.5 billion years ago, when a Mars-sized body collided with the young Earth in a cataclysmic impact. The debris from this collision coalesced in orbit around Earth, gradually accumulating to form the Moon. This giant impact hypothesis explains many of the Moon's unusual properties, including its relatively low density, its lack of a significant iron core, and the chemical similarity between lunar rocks and Earth's mantle. The Moon has no atmosphere, no liquid water, and no protection from the harsh radiation of space. Its surface is covered in a layer of fine, powdery dust called regolith, created by billions of years of meteorite impacts. Daytime temperatures on the Moon's equator can reach about 250 degrees Fahrenheit, while nighttime temperatures plummet to around -208 degrees. The Moon's gravitational pull is about 1/6 that of Earth's, so an astronaut weighing 180 pounds on Earth would weigh only about 30 pounds on the Moon. Despite its barren appearance, the Moon may harbor a valuable resource, water ice. In the permanently shadowed craters near the Moon's poles, where sunlight never reaches, temperatures drop to as low as -400 degrees Fahrenheit. In these frigid depths, water ice delivered by comets and meteorites over billions of years may have accumulated and survived. Detecting and extracting this water could be crucial for future lunar exploration, as water can be used for drinking, growing food, and even manufacturing rocket fuel. After the Moon landings, human space exploration shifted its focus to low Earth orbit. Space stations became the new frontier, permanent outposts in space where astronauts could live and work for extended periods. The first space stations were launched in the early 1970s, and they demonstrated that humans could survive in microgravity for weeks and even months at a time. The International Space Station, or ISS, which has been continuously inhabited since November 2000, is the largest structure ever built in space. It orbits Earth at an altitude of roughly 250 miles, traveling at about 17,500 miles per hour and completing one orbit every 90 minutes. This means that astronauts aboard the ISS experience 16 sunrises and 16 sunsets every single day. The ISS has been home to astronauts and cosmonauts from numerous countries, serving as a laboratory for scientific research in microgravity, a test bed for technologies needed for deep space exploration, and a symbol of international cooperation. Life aboard the ISS is unlike anything on Earth. In microgravity, there is no up or down. Astronauts float freely through the station's modules, sleeping in sleeping bags strapped to the walls, eating food from pouches, and exercising for at least 2 hours every day to counteract the effects of weightlessness on their muscles and bones. Without regular exercise, astronauts can lose up to 1% of their bone density per month in space, a rate roughly 10 times faster than osteoporosis on Earth. Their muscles also atrophy, their cardiovascular systems become less efficient, and their vision can be affected by increased intracranial pressure. Understanding and mitigating these health effects is crucial for any future missions to Mars, which could require astronauts to spend 6 to 9 months in transit each way. Water behaves strangely in microgravity. Instead of flowing downward as it does on Earth, water forms floating spheres that drift through the air. Tears do not roll down an astronaut's cheeks, they accumulate into growing blobs of water around the eyes. Flames burn as spheres instead of the familiar teardrop shape, because there is no convection to draw hot air upward and fresh air inward. These seemingly small observations have led to important scientific discoveries about fluid dynamics, combustion, and other physical processes. The ISS has also served as a platform for observing Earth and the cosmos. Astronauts aboard the station have taken hundreds of thousands of photographs of our planet, documenting everything from city lights to volcanic eruptions to the aurora borealis. These images have provided valuable data for environmental scientists and have given the general public a new perspective on the beauty and fragility of our home planet. Now let us look forward and consider the future of human space exploration. Mars is the next great destination. Plans are being developed to send humans to the Red Planet within the coming decades. The challenges are enormous. Mars is, on average, about 140 million miles from Earth, and a one-way trip using current propulsion technology would take roughly 6 to 9 months. Communication delays between Earth and Mars can be as long as 24 minutes one way, meaning that astronauts on Mars would need to be largely self-sufficient, unable to rely on real-time guidance from mission control. They would need to produce their own food, recycle their own water and air, and deal with medical emergencies without the possibility of emergency evacuation. The radiation environment on Mars is also a significant concern. Without a thick atmosphere or a global magnetic field, the Martian surface is exposed to harmful cosmic rays and solar radiation. Despite these challenges, the dream of setting foot on Mars continues to inspire engineers, scientists, and explorers around the world. The establishment of a permanent human presence on Mars, and eventually the terraforming of the planet to make it more Earth-like, represents one of the most ambitious long-term goals of our species. Whether it will be achieved in our lifetimes remains to be seen, but the work being done today is laying the foundation for that future. Beyond Mars, the outer solar system beckons. Missions to Jupiter's moon Europa, Saturn's moon Titan and Enceladus, and even the ice giants Uranus and Neptune are being planned or proposed. Each of these destinations offers unique scientific opportunities and the potential for groundbreaking discoveries. The exploration of the outer solar system will likely rely on robotic spacecraft for the foreseeable future, given the immense distances and harsh conditions involved, and beyond our solar system. The challenges of interstellar travel are almost incomprehensibly vast. Even the nearest star system is over 4 light-years away, and with current technology, a journey to Proxima Centauri would take tens of thousands of years. Revolutionary new propulsion technologies, such as solar sails, nuclear pulse propulsion, or even theoretical concepts like the Alcubierre warp drive, would be needed to make interstellar travel feasible within a human lifetime. Whether such technologies are possible remains an open question, but the history of human innovation suggests that we should never underestimate our ability to overcome seemingly impossible obstacles. Let us close this first part of our journey through the cosmos with a reflection on what we have learned so far. We have traveled from the blazing heart of our sun to the frozen wastelands of the outer solar system. We have witnessed the birth and death of stars, the formation of black holes, and the discovery of gravitational waves. We have contemplated the origin of the universe itself, from the Big Bang to the cosmic dark ages to the formation of the first galaxies. We have grappled with the mysteries of dark matter and dark energy, which together make up 95% of the universe yet remain completely unknown. We have bent our minds around the strange predictions of Einstein's theories, time dilation, curved spacetime, and the ultimate speed limit of the cosmos. We have considered the search for extraterrestrial life and the profound implications of the Fermi paradox. And we have traced the history of human space exploration, from the first satellite to the International Space Station, and looked forward to the future missions that will take us to Mars and beyond. But this is only the beginning. The universe is far stranger, far more beautiful, and far more terrifying than anything we have covered so far. There are phenomena out there that defy imagination, magnetars with magnetic fields strong enough to erase credit cards from the distance of the moon, rogue planets wandering through the darkness between stars, galaxies that are consuming each other in slow-motion collisions lasting billions of years, and cosmic structures so vast that they challenge our fundamental understanding of the universe. The fabric of reality is woven with threads of mystery, and every answer we find leads to a dozen new questions. The universe does not give up its secrets easily. But that is precisely what makes the exploration of space so compelling. It is the ultimate adventure, a journey without end into the infinite unknown. Let us begin this second chapter with one of the most violent and terrifying objects in the known universe, the magnetar. A magnetar is a type of neutron star, but it is not an ordinary neutron star. It possesses a magnetic field so extraordinarily powerful that it defies comprehension. The magnetic field of a typical refrigerator magnet is about 100 Gauss. The magnetic field of the Earth is about half a Gauss. The magnetic field of a standard neutron star is around 1,000,000,000,000 Gauss, but a magnetar's magnetic field can reach up to 1,000,000,000,000 Gauss, a 1 followed by 15 zeros. This makes magnetars the most powerfully magnetized objects in the known universe. To understand just how extreme this is, consider the following. If a magnetar were located halfway between the Earth and the Moon, roughly 120,000 miles away, its magnetic field would be strong enough to erase every credit card on the planet. It would wipe every magnetic strip, every hard drive, every piece of magnetically stored data on Earth from a distance of over 100,000 miles. Get closer and the effects become far more dramatic. At a distance of about 600 miles from a magnetar, the magnetic field would be strong enough to distort the electron clouds around atoms in your body, effectively dissolving the molecular bonds that hold you together. You would not be crushed or burned, you would be disassembled at the atomic level. Magnetars also produce occasional bursts of energy called starquakes, sudden rearrangements of the star's crust that release enormous amounts of gamma radiation. On December 27, 2004, a magnetar located about 50,000 light-years away in our own galaxy released a burst of energy so powerful that it briefly disrupted Earth's ionosphere, even from halfway across the Milky Way. The burst released more energy in 1/10 of a second than our Sun produces in 250,000 years. Had this magnetar been located within 10 light-years of Earth, the radiation would have been catastrophic for life on our planet. Fortunately, no known magnetars exist anywhere near our solar system. Magnetars are thought to be relatively rare. Only about 30 have been confirmed in our galaxy, though more likely exist undetected. They are born from the most massive stars, under conditions that produce unusually strong magnetic fields during the supernova explosion. A magnetar's intense magnetic field decays over time, and after about 10,000 years, it fades enough that the magnetar can no longer produce its characteristic bursts. It then becomes a more ordinary neutron star, quietly spinning in the darkness. Now let us talk about another class of extreme cosmic phenomena, gamma-ray bursts. These are the most energetic explosions in the universe since the Big Bang itself. A gamma-ray burst is a sudden, intense flash of gamma radiation that can last anywhere from a fraction of a second to several minutes. During that brief window, a single gamma-ray burst can release more energy than the Sun will produce in its entire 10-billion-year lifetime. They are so bright that they can be detected from billions of light-years away, making them visible across nearly the entire observable universe. Gamma-ray bursts come in two varieties. Short-duration gamma-ray bursts lasting less than about 2 seconds are believed to be caused by the merger of two neutron stars or a neutron star and a black hole. When these ultradense objects spiral together and collide, the resulting cataclysm produces a brief but incredibly intense flash of gamma radiation, along with gravitational waves and a shower of heavy elements. In fact, neutron star mergers are now believed to be the primary source of many of the heaviest elements in the universe, including gold and platinum. The gold in your jewelry, the platinum in catalytic converters, the rare earth elements in your electronics, much of it may have been forged in the violent collisions of neutron stars billions of years ago. Long-duration gamma-ray bursts, lasting more than about 2 seconds, are associated with the deaths of extremely massive stars at least 20 to 30 times the mass of our Sun. When these behemoths collapse at the end of their lives, they can form a rapidly spinning black hole surrounded by a disk of superheated material. Jets of energy and matter are launched along the rotational axis at nearly the speed of light, and if one of these jets happens to be pointed directly at Earth, we detect it as a gamma-ray burst. The narrow focus of these jets means that we only see a small fraction of all gamma-ray bursts that occur. For every one we detect, many more are beaming their energy in other directions, invisible to us. If a gamma-ray burst occurred within our own galaxy and its jet were aimed at Earth, the consequences could be devastating. The intense radiation would strip away a significant portion of our ozone layer, exposing the surface to harmful ultraviolet radiation from the sun. This could trigger mass extinctions of marine and terrestrial life. Some scientists have speculated that a gamma-ray burst may have been responsible for the Ordovician mass extinction about 450 million years ago, which wiped out roughly 60% of all marine species. However, this remains speculative, and the probability of a gamma-ray burst occurring close enough to Earth to cause significant damage is extremely low. From gamma-ray bursts, let us move to another extraordinary phenomenon, quasars. A quasar is the extremely luminous core of a distant galaxy, powered by a supermassive black hole that is actively devouring enormous quantities of matter. As material falls toward the black hole, it forms a swirling disk of superheated gas called an accretion disk. Friction and gravitational forces within this disk heat the material to temperatures of millions of degrees, causing it to radiate prodigious amounts of energy across the electromagnetic spectrum, from radio waves to visible light to X-rays. A single quasar can outshine its entire host galaxy by a factor of 100 or more, making it visible across billions of light-years of space. Quasars were first discovered in the early 1960s, and they initially baffled astronomers. They appeared as point-like sources of light, similar to stars, but their spectra showed enormous redshifts, indicating that they were receding from us at tremendous speeds and were therefore located at vast distances. The amount of energy they were producing from such small regions of space seemed impossible by any known mechanism. It was not until the connection between quasars and supermassive black holes was established that their extraordinary luminosity was explained. The most luminous quasars produce energy at a rate equivalent to the simultaneous output of trillions of suns. They are the brightest sustained sources of electromagnetic radiation in the universe. The most distant quasars discovered so far are seen as they existed when the universe was less than 1 billion years old, making them invaluable tools for studying the conditions of the early universe. The fact that supermassive black holes massive enough to power these quasars already existed so early in cosmic history is one of the great puzzles of modern astrophysics. How these black holes grew so large so quickly remains an area of active research. As a quasar consumes the available gas in its vicinity, it eventually runs out of fuel and fades. Most quasars were active in the early universe, and the quasar population has declined dramatically over cosmic time. Our own galaxy, the Milky Way, likely went through a quasar phase billions of years ago, when its central supermassive black hole was actively feeding. Today, Sagittarius A star is relatively quiet, but it could potentially be reactivated if a sufficient supply of gas were to fall into its vicinity, for example, during the future collision with the Andromeda galaxy. Let us now explore something that sounds like pure science fiction, but is grounded in the mathematics of Einstein's general relativity, wormholes. A wormhole, technically known as an Einstein-Rosen bridge, is a theoretical tunnel through spacetime that could connect two distant points in the universe. Imagine folding a piece of paper so that two distant points on the paper are brought close together, and then poking a hole through both layers. The hole is the wormhole, a shortcut through spacetime that could, in theory, allow faster than light travel between two widely separated locations. The mathematics of general relativity permits the existence of wormholes, but whether they actually exist in nature is entirely unknown. Even if they do exist, they would likely be incredibly unstable, collapsing the instant any matter attempted to pass through them. To keep a wormhole open and traversable, exotic matter with negative energy density would be required, a substance that may not exist in any practical sense, though quantum mechanics suggests that negative energy can exist in very small quantities under very specific conditions. Some theoretical physicists have speculated that wormholes could also function as time machines, connecting not just two different points in space, but two different points in time. This raises a host of paradoxes, most famously the grandfather paradox, in which a time traveler goes back in time and prevents their own grandparent from meeting, thereby preventing their own birth. How or whether physics resolves such paradoxes is one of the deepest unsolved questions in theoretical physics. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel into the past, though no proof of this conjecture has been found. While wormholes remain firmly in the realm of theory, their study has led to important insights into the nature of spacetime, gravity, and the relationship between general relativity and quantum mechanics. They serve as thought experiments that push the boundaries of our understanding and challenge us to think about the universe in radically new ways. Now let us turn our attention to one of the most extraordinary discoveries of recent decades, the sheer abundance and diversity of planets orbiting other stars. For most of human history, we had no way of knowing whether planets existed beyond our own solar system. The first confirmed detection of an exoplanet orbiting a Sun-like star came in 1995, when astronomers discovered a Jupiter-mass planet orbiting the star 51 Pegasi, located about 50 light-years from Earth. This planet, designated 51 Pegasi b, was a so-called hot Jupiter, a gas giant orbiting extremely close to its parent star, completing one orbit in just over 4 days. Its discovery was revolutionary because it challenged existing models of planetary formation, which predicted that gas giants could only form far from their stars. Since that initial discovery, thousands of exoplanets have been confirmed, and the pace of discovery continues to accelerate. The Kepler Space Telescope, which operated from 2009 to 2018, was responsible for discovering the majority of known exoplanets. It did so by monitoring the brightness of over 150,000 stars simultaneously, looking for the tiny, periodic dips in brightness that occur when a planet passes in front of its star, a technique known as the transit method. Kepler's data revealed that planets are extraordinarily common. On average, every star in the Milky Way has at least one planet, and many have multiple planets. Extrapolating from Kepler's results, astronomers estimate that there are at least 100 billion planets in our galaxy alone. The diversity of exoplanets is staggering. Hot Jupiters orbit so close to their stars that their atmospheres are heated to thousands of degrees. Super-Earths, rocky planets larger than Earth but smaller than Neptune, are common in other star systems but absent from our own. Mini-Neptunes with thick atmospheres of hydrogen and helium are the most common type of planet in the galaxy. And then there are the truly exotic worlds, planets made entirely of diamond, planets that orbit two suns like the fictional Tatooine, planets that are tidally locked so that one hemisphere is permanently scorched while the other is locked in eternal night, and rogue planets that drift through interstellar space, unbound to any star at all. Rogue planets are particularly fascinating. These are worlds that have been gravitationally ejected from their parent star systems, sent hurtling into the void between stars. Without a star to warm them, their surfaces are frozen and dark, and yet some rogue planets might still harbor conditions suitable for life. If a rogue planet is large enough to retain a thick atmosphere, the greenhouse effect could potentially keep its surface warm enough for liquid water. Alternatively, tidal heating from moons could provide energy to a subsurface ocean. The number of rogue planets in the Milky Way is estimated to be in the billions, possibly exceeding the number of planets orbiting stars. The darkness between the stars may be far more populated than we ever imagined. Among the most exciting exoplanet discoveries are those in the so-called habitable zone, the range of orbital distances from a star where conditions might be right for liquid water to exist on a planet's surface. The TRAPPIST-1 system, discovered in 2017, contains 7 Earth-sized planets orbiting a small, cool red dwarf star about 40 light-years from Earth. At least 3 of these planets are in the habitable zone. The system has become one of the most studied in exoplanet science, and it will be a prime target for atmospheric characterization by the James Webb Space Telescope. Speaking of which, let us talk about the James Webb Space Telescope, one of the most ambitious and powerful scientific instruments ever created. The James Webb Space Telescope, or JWST, was launched on December 25, 2021, after decades of development. It is the successor to the Hubble Space Telescope, but it is far more powerful. Its primary mirror is 21 feet in diameter, roughly 6 times the collecting area of Hubble's mirror, and it is optimized for infrared observations, allowing it to see through clouds of dust and gas that block visible light. It is stationed at a point in space called the second Lagrange point, about 1 million miles from Earth, where it is shielded from the sun's heat and light by a tennis court-sized sunshield that keeps the telescope at an operating temperature of roughly -370 degrees Fahrenheit. The JWST has already transformed our understanding of the universe. Its first deep-field image, released in July 2022, revealed thousands of galaxies in a tiny patch of sky no larger than a grain of sand held at arm's length. Some of these galaxies are seen as they appeared over 13 billion years ago, when the universe was in its infancy. The clarity and depth of the image surpassed anything Hubble had ever achieved, and it was obtained in a fraction of the time. The JWST is designed to address some of the most fundamental questions in astronomy. How did the first stars and galaxies form? What were the conditions like in the early universe? How do stars and planetary systems form and evolve? And crucially, what are the atmospheres of potentially habitable exoplanets composed of? By analyzing the light that passes through or is emitted by exoplanet atmospheres, the JWST can identify the chemical fingerprints of specific molecules, water vapor, carbon dioxide, methane, and potentially even biosignatures like oxygen or ozone. If life exists on a nearby exoplanet and has altered its atmosphere in detectable ways, the JWST may be the instrument that finds the first evidence. But the JWST is not the only revolutionary telescope at our disposal. Let us take a moment to appreciate the instruments that have shaped our view of the cosmos. The Hubble Space Telescope, launched in 1990, has been one of the most productive scientific instruments in history. Despite a well-publicized flaw in its primary mirror that initially produced blurry images, a flaw that was corrected by a servicing mission in 1993, Hubble has made over 1.5 million observations and contributed to more than 18,000 scientific papers. Its images of distant galaxies, nebulae, and other celestial objects have become iconic, fundamentally shaping the public's perception of the universe. Hubble played a key role in determining the rate at which the universe is expanding, in discovering that the expansion is accelerating, and in providing evidence for the existence of supermassive black holes at the centers of galaxies. Ground-based telescopes have also made enormous strides. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and the Atacama Large Millimeter Array, also in Chile, are among the most powerful observatories on Earth. The Event Horizon Telescope, which produced the first image of a black hole's shadow in 2019, is not a single telescope, but a network of radio telescopes spanning the globe, linked together to function as a single Earth-sized telescope through a technique called very long baseline interferometry. And even more powerful telescopes are on the horizon. The Extremely Large Telescope, currently under construction in Chile, will have a primary mirror nearly 130 feet in diameter, 5 times larger than the largest existing optical telescopes. When completed, it will be able to directly image exoplanets orbiting nearby stars and study their atmospheres in unprecedented detail. The Vera C. Rubin Observatory, also in Chile, will conduct a decade-long survey of the entire visible sky, cataloging billions of stars and galaxies and tracking objects that change or move over time. These instruments represent the pinnacle of human ingenuity, and they are opening windows onto the universe that previous generations could never have imagined. Now let us venture into the realm of theoretical physics, the frontier where observation ends and imagination, guided by mathematics, begins. One of the most ambitious goals of modern physics is the development of a theory of everything, a single, unified framework that describes all the fundamental forces of nature and all the elementary particles. Currently, physics operates with two enormously successful but fundamentally incompatible theories. General relativity, developed by Einstein, describes gravity and the large-scale structure of the universe. Quantum mechanics describes the behavior of matter and energy at the smallest scales, atoms, subatomic particles, and photons. Both theories have been tested to extraordinary precision and have never been found to be wrong within their respective domains. But when physicists try to combine them, when they try to apply quantum mechanics to gravity or describe the singularity at the center of a black hole, the mathematics breaks down, producing nonsensical infinities. String theory is one of the leading candidates for a theory of everything. It proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional vibrating strings of energy. Different vibrational patterns of these strings correspond to different particles, electrons, quarks, photons, and even the hypothetical graviton, the particle that would carry the gravitational force. String theory naturally incorporates gravity and quantum mechanics, which is one of its most appealing features. However, string theory requires the existence of extra spatial dimensions beyond the three we experience. Depending on the version of the theory, there may be 10 or 11 dimensions of space and time. The extra dimensions, if they exist, are thought to be curled up so small that they are undetectable by current experiments. This makes string theory extremely difficult, perhaps impossible, to test directly with existing technology. Critics argue that a theory that cannot be tested is not truly a scientific theory at all, but proponents counter that the mathematical elegance and internal consistency of string theory are powerful arguments in its favor. Another fascinating theoretical concept is the multiverse, the idea that our universe may be just one of an enormous, perhaps infinite, number of universes, each with its own physical laws, constants, and initial conditions. The multiverse concept arises naturally from several different areas of physics. Inflationary cosmology suggests that the process of inflation that occurred in the first fraction of a second after the Big Bang may not have stopped everywhere at once. Instead, inflation may be eternal, with different regions of space stopping inflation at different times and forming separate bubble universes, each with its own properties. String theory, with its vast landscape of possible solutions, estimated at 10 to the 500th power, suggests that each solution could correspond to a different universe with different physical laws. If the multiverse exists, it could provide an explanation for one of the deepest puzzles in physics, the fine-tuning of the fundamental constants of nature. The laws of physics in our universe appear to be exquisitely fine-tuned for the existence of complex structures, including life. If the strength of gravity, the mass of the electron, or the charge of the proton were even slightly different, atoms might not form, stars might not ignite, and the chemistry necessary for life might not be possible. In a single universe, this fine-tuning seems like an astonishing coincidence. But in a multiverse, where every possible combination of physical constants is realized somewhere, it is not surprising that we find ourselves in a universe where the constants allow for our existence. We could not exist in a universe that did not support life, so of course, we observe a universe that does. This reasoning is known as the anthropic principle. The multiverse remains highly speculative, and many physicists are uncomfortable with the concept because it may be inherently untestable. If other universes exist but are fundamentally inaccessible to observation, can we ever know whether they are real? This question sits at the intersection of physics and philosophy, and it is unlikely to be resolved anytime soon. Let us now turn to a topic that is both scientifically profound and deeply practical: the threat posed to Earth by asteroids and comets. Throughout its history, Earth has been bombarded by objects from space. The craters on the Moon, preserved in pristine condition due to the absence of erosion, provide a vivid record of the violence of this bombardment. Earth has experienced the same bombardment, but most of the evidence has been erased by geological processes, plate tectonics, erosion, volcanic activity, and the growth of vegetation. But some scars remain. The Chicxulub crater, buried beneath the Yucatan Peninsula of Mexico, is approximately 110 miles in diameter and was formed 66 million years ago by the impact of an asteroid roughly 6 miles across. This impact is widely believed to have caused the mass extinction that wiped out the non-avian dinosaurs and approximately 75% of all species on Earth. The energy released by the impact was equivalent to roughly 10 billion nuclear weapons detonating simultaneously. It triggered massive earthquakes, tsunamis hundreds of feet tall, global wildfires, and a nuclear winter effect as dust and debris blocked sunlight for months or even years, causing temperatures to plummet and devastating the global food chain. The Chicxulub impact was a civilization-ending event, or rather it would have been had civilizations existed at the time. And while an impact of that magnitude is extremely rare, occurring perhaps once every 100 million years, smaller impacts are far more frequent. The Tunguska event of 1908, in which a small asteroid or comet fragment exploded in the atmosphere above a remote region of Siberia, flattened an estimated 80 million trees over an area of 830 square miles. Had this event occurred over a major city, the death toll could have been in the millions. Today, astronomers are actively searching for near-Earth objects, asteroids and comets whose orbits bring them close to Earth's orbit. Numerous surveys are tracking these objects, cataloging their sizes, orbits, and potential threat levels. As of now, no known asteroid poses a significant risk of impact in the foreseeable future, but the search is ongoing and new objects are being discovered regularly. In September 2022, a spacecraft was deliberately crashed into a small asteroid moon called Dimorphos in the first ever test of planetary defense technology. The mission successfully altered the asteroid's orbit, demonstrating that it is possible, in principle, to deflect a potentially hazardous asteroid before it reaches Earth. This was a milestone in planetary defense, the first time humanity had intentionally changed the trajectory of a celestial body. Other proposed methods of asteroid deflection include gravitational tractors, spacecraft that would hover near a threatening asteroid and gradually alter its course through gravitational attraction, nuclear detonation, which could vaporize a portion of the asteroid's surface and produce a rocket-like thrust, and even painting one side of the asteroid white, which would change the way it absorbs and re-emits solar radiation, slowly nudging it off course over time. The effectiveness of these methods depends on the size of the asteroid and the amount of warning time available, underscoring the importance of early detection. Let us now leave the subject of cosmic threats and turn to something more sublime: the nebulae, those vast, luminous clouds of gas and dust that are among the most beautiful objects in the universe. Nebulae come in several varieties. Emission nebulae glow with their own light, as the gas within them is heated and ionized by nearby hot stars. The Orion Nebula, one of the brightest nebulae in the sky and visible to the naked eye as a fuzzy patch in the constellation Orion, is a stellar nursery where new stars are being born right now. It is located about 1,340 light-years from Earth and spans roughly 24 light-years across. Deep within the Orion Nebula, dense knots of gas and dust are collapsing under their own gravity, forming protostars, embryonic stars that have not yet ignited nuclear fusion. Some of these protostars are surrounded by disks of gas and dust that may eventually form planetary systems similar to our own. Reflection nebulae do not produce their own light, but instead glow by reflecting the light of nearby stars. The beautiful blue nebula surrounding the Pleiades star cluster is a well-known example. Dark nebulae are dense clouds of dust that block the light of stars and nebulae behind them, appearing as dark patches against the brighter background. The Horsehead Nebula in Orion is one of the most famous dark nebulae, its distinctive shape recognizable in countless astronomical images. Planetary nebulae, despite their name, have nothing to do with planets. They are shells of gas expelled by dying sun like stars as they shed their outer layers near the end of their lives. The remaining core of the star, now a hot white dwarf, illuminates the expanding shell from within, creating exquisitely beautiful structures. The Ring Nebula, the Cat's Eye Nebula, and the Helix Nebula are all stunning examples of planetary nebulae. These structures are relatively short-lived in astronomical terms, lasting only about 10 to 20,000 years before the gas disperses into interstellar space. Supernova remnants are the expanding debris clouds left behind after a massive star explodes. The Crab Nebula, located about 6,500 light-years from Earth, is the remnant of a supernova that was observed on Earth in the year 1054. At its center lies a pulsar, a rapidly spinning neutron star that rotates about 30 times per second, emitting beams of radiation with each rotation. The Crab Nebula is still expanding, and the energy from the central pulsar continues to illuminate the surrounding gas, creating one of the most studied objects in all of astronomy. Now let us discuss something that touches every aspect of our lives yet is often overlooked: the sun's influence on our planet beyond simple warmth and light. We are speaking of space weather. The sun is not a static, unchanging object. It is a dynamic, active star that undergoes regular cycles of activity. Approximately every 11 years, the sun's magnetic field undergoes a complete reversal, with the north and south magnetic poles switching places. This cycle of magnetic activity is accompanied by changes in the number and intensity of sunspots, dark, cooler regions on the sun's surface where intense magnetic fields inhibit convection and reduce the surface temperature. During solar maximum, when the sun is most active, the number of sunspots increases dramatically, and the sun produces more solar flares and coronal mass ejections. A solar flare is a sudden, intense burst of electromagnetic radiation from the sun's surface, caused by the release of magnetic energy stored in the sun's atmosphere. Solar flares can produce radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The most powerful flares, classified as X-class flares, can disrupt radio communications, degrade GPS accuracy, and pose a radiation hazard to astronauts in space. Coronal mass ejections, or CMEs, are even more dramatic. A CME is a massive bubble of magnetized plasma ejected from the sun's corona, its outermost atmosphere, at speeds ranging from hundreds of thousands to millions of miles per hour. When a CME is directed at Earth, it can interact with our planet's magnetic field, compressing it on the sun-facing side and stretching it on the night side. This interaction can produce spectacular auroral displays, the northern and southern lights, as charged particles from the CME spiral along Earth's magnetic field lines and collide with atoms in the upper atmosphere, causing them to glow. But severe CMEs can also cause serious damage. In March 1859, the most powerful geomagnetic storm ever recorded, known as the Carrington Event, struck Earth. The storm was caused by an enormous CME that reached Earth in just 17.5 hours, far faster than typical. The resulting geomagnetic disturbance was so intense that telegraph systems across the world failed. Some telegraph operators received electric shocks, and telegraph machines reportedly continued to operate even after being disconnected from their power supplies, driven solely by the currents induced by the storm. Auroras were visible as far south as the Caribbean. If a Carrington-level event were to occur today, the consequences could be catastrophic. Modern civilization is far more dependent on electronic technology than the world of 1859. A severe geomagnetic storm could damage or destroy transformers in the electrical grid, potentially leaving hundreds of millions of people without power for weeks or even months. It could disable satellites, disrupt air travel, and cause trillions of dollars in economic damage. Scientists estimate that a Carrington-level event has roughly a 12% chance of occurring in any given decade, meaning it is not a matter of if but when. Monitoring and predicting space weather has become an increasingly important priority. Spacecraft positioned between the Earth and the Sun provide early warning of incoming CMEs, giving operators of power grids and satellite systems time to take protective measures. But our current forecasting capabilities are limited, and significant investment in space weather monitoring and preparedness is needed to protect our technological infrastructure from the sun's fury. Let us now journey to the very edge of our solar system and beyond, to a region that marks the boundary between our sun's domain and interstellar space. The sun emits a constant stream of charged particles called the solar wind, which flows outward in all directions at speeds of roughly 1 million miles per hour. This solar wind creates a vast bubble of charged particles and magnetic fields around the sun called the heliosphere. The heliosphere extends far beyond the orbit of Pluto, enveloping the entire solar system in a protective cocoon that shields us from some of the harshest radiation of interstellar space. At the outer edge of the heliosphere, the solar wind slows down as it encounters the pressure of the interstellar medium, the gas and dust that fills the space between stars. The point where the solar wind slows to subsonic speeds is called the termination shock. Beyond the termination shock lies the heliosheath, a turbulent region where the solar wind is compressed and heated. And beyond the heliosheath lies the heliopause, the boundary where the solar wind is finally halted by the interstellar medium. The heliopause marks the true edge of the sun's sphere of influence and the beginning of interstellar space. 2 spacecraft have crossed the heliopause and entered interstellar space. Voyager 1 crossed the boundary in August 2012, at a distance of roughly 11.3 billion miles from the sun. Voyager 2 followed in November 2018. Both spacecraft were launched in 1977 and have been traveling through space for over 4.5 decades. They continue to send back data, though their power supplies plutonium-based radioisotope thermoelectric generators are gradually weakening, and they are expected to cease scientific operations sometime in the late 2020s or early 2030s. The Voyager spacecraft carry golden records, phonograph records plated with gold, containing sounds, images, and greetings from Earth in 55 languages. These records were intended as messages to any extraterrestrial intelligence that might someday encounter the spacecraft. Given the vast distances of interstellar space, the Voyager probes will drift among the stars for billions of years, long after our sun has exhausted its fuel and died. They are, in a very real sense, humanity's message in a bottle, cast into the cosmic ocean. Beyond the heliopause, far out in the cold darkness, lies the Oort cloud, a vast spherical shell of icy bodies that is believed to extend from roughly 2,000 to 100,000 astronomical units from the sun. An astronomical unit is the average distance from the Earth to the sun, about 93 million miles. So the outer edge of the Oort cloud is nearly 2 light-years from the sun, almost halfway to the nearest star. The Oort cloud is thought to contain trillions of icy bodies, the remnants of the primordial solar nebula from which our solar system formed. Occasionally, gravitational perturbations from passing stars or the tidal forces of the Milky Way dislodge one of these icy bodies, sending it plunging inward toward the sun on a highly elongated orbit. When it gets close enough to the sun, the ice begins to sublimate, producing a glowing coma and a spectacular tail. We call these objects comets. Comets have been observed and recorded throughout human history. Ancient civilizations often regarded them as omens, harbingers of doom, war, or the death of kings. Today, we understand them as pristine remnants of the early solar system, carrying within them the same volatile compounds and organic molecules that existed 4.5 billion years ago. Studying comets gives us a window into the conditions that prevailed when our solar system was forming. In 2014, the Rosetta spacecraft achieved something remarkable. It entered orbit around a comet and deployed a lander named Philae to the comet's surface. The comet, known as 67P/Churyumov-Gerasimenko, turned out to be a bizarre, duck-shaped body covered in cliffs, boulders, and jets of gas erupting from its surface as it approached the sun. Rosetta's observations revealed that the comet's water had a different isotopic composition than Earth's ocean water, suggesting that comets may not have been the primary source of Earth's water, as some theories had proposed. However, the mission also detected the amino acid glycine and phosphorus, both essential building blocks of life, suggesting that comets could have delivered some of the raw materials for life to the early Earth. Let us now contemplate the far future, the ultimate fate of the universe. This is a subject that fills some people with awe and others with existential dread, but it is one of the most profound questions that science can address. The fate of the universe depends on several factors, including the total density of matter and energy, the nature of dark energy, and the geometry of spacetime. Based on current observations, the most likely scenario is what physicists call the heat death of the universe, a slow, inexorable decline into maximum entropy and absolute darkness. Here is how it unfolds. Stars will continue to form for roughly another 100 trillion years, but the supply of hydrogen gas from which new stars are made is finite. Eventually, the last stars will burn out and no new ones will form. The universe will be filled with the remnants of dead stars, white dwarfs, neutron stars, and black holes, all slowly cooling in an expanding, increasingly empty cosmos. Over unimaginably long timescales, perhaps 10 to the 40th power years, protons and neutrons may themselves decay, if certain predictions from particle physics are correct. If proton decay occurs, all ordinary matter will eventually disintegrate, leaving behind a diffuse fog of electrons, positrons, neutrinos, and photons. Black holes will be the last significant objects to survive, but even black holes are not eternal. Stephen Hawking showed in 1974 that black holes emit radiation, now called Hawking radiation, due to quantum mechanical effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly lose mass and shrink. The process is extraordinarily slow. A stellar mass black hole would take roughly 10 to the 67th power years to evaporate completely. A supermassive black hole like Sagittarius A star would take roughly 10 to the 100th power years, a one followed by 100 zeros. But given enough time, every black hole in the universe will eventually evaporate, releasing its energy as a faint whisper of radiation. After the last black hole evaporates, the universe will consist of nothing but a dilute gas of elementary particles and low-energy photons, drifting ever further apart in an ever-expanding void. The temperature of the universe will asymptotically approach absolute zero but never quite reach it. Nothing will happen, no stars will shine, no life will stir. No new structures will form. The universe will have reached a state of maximum entropy, perfect thermodynamic equilibrium, from which no further work or change is possible. This is the heat death. It is a bleak vision, but it is important to note that it lies inconceivably far in the future. Even the evaporation of the last black holes occurs on timescales so vast that the current age of the universe, 13.8 billion years, is essentially zero by comparison. If the history of the universe from the Big Bang to the present were compressed into a single second, the time remaining until the heat death would be longer than the entire age of the universe raised to a power of a power of a power, a number so large that it has no meaningful representation in everyday language. There are alternative scenarios for the fate of the universe, though they are currently considered less likely. In the Big Crunch scenario, the expansion of the universe would eventually reverse, and the universe would contract, growing hotter and denser until everything collapsed back into a singularity, a mirror image of the Big Bang. Some speculative theories suggest that this collapse could be followed by a new Big Bang, giving rise to a new universe in an endless cycle of birth, death, and rebirth. This is the Big Bounce hypothesis. In the Big Rip scenario, the influence of dark energy would increase over time, eventually overwhelming all other forces. First, galaxies would be torn apart, then stars, then planets, then atoms, and finally spacetime itself would be ripped apart in a catastrophic finale. The Big Rip, if it occurs, could happen in as little as 20 billion years, though current observations suggest that dark energy is constant in strength, making this scenario unlikely. And then there is the possibility that the universe could undergo a phased transition, a sudden, catastrophic change in the fundamental properties of the vacuum of space. If the current vacuum state of the universe is not the lowest energy state, if it is what physicists call a false vacuum, then a random quantum fluctuation could trigger a transition to the true vacuum state. This transition would propagate outward at the speed of light as a bubble of destruction, within which the laws of physics would be fundamentally different. All matter, all structures, all life within the bubble would be annihilated. There would be no warning and no escape. This scenario, terrifying as it sounds, is considered extremely unlikely, and even if it were possible, the probability of it occurring at any given time is vanishingly small. Let us step back from these cosmic eschatologies and return to something more immediate and human, the profound psychological and philosophical impact of space exploration. Astronauts who have seen Earth from space often describe a transformative experience known as the overview effect. From orbit, national borders are invisible. Wars, political conflicts, and social divisions seem absurd. The Earth appears as a small, fragile, beautiful sphere of blue and white, hanging in the black void of space, the only home that humanity has ever known. Many astronauts have reported that seeing Earth from this perspective filled them with a profound sense of interconnectedness, humility, and responsibility. One of the most famous photographs ever taken encapsulates this perspective. In 1990, as the Voyager 1 spacecraft was leaving the solar system, it was commanded to turn its camera back toward Earth and take a final photograph. The resulting image showed Earth as a tiny, pale blue dot, less than a pixel in size, suspended in a beam of sunlight against the vast darkness of space. The astronomer Carl Sagan, who had championed the idea of taking the photograph, wrote eloquently about its significance. He noted that every human being who has ever lived, every king and peasant, every hero and coward, every creator and destroyer of civilization lived out their lives on that tiny speck. He urged humanity to treat each other with kindness and to preserve and cherish the pale blue dot, the only home we have ever known. This perspective, the cosmic perspective, is perhaps the greatest gift that space exploration has given us. It is not a telescope or a spacecraft or a piece of technology. It is a way of seeing ourselves and our world in the context of the vast, ancient, and magnificent universe we inhabit. It is a reminder that we are small but not insignificant, that we are brief but not without purpose, that the same atoms that compose our bodies were forged in the hearts of stars billions of years ago, and that when we die, those atoms will return to the cosmos, to be recycled into new stars, new planets, and perhaps, someday, new life. Let us also consider the concept of cosmic time, the sheer scale of time over which the universe operates. If you compress the entire history of the universe, from the Big Bang to the present, into a single calendar year, with the Big Bang occurring at midnight on January 1st and the present moment at midnight on December 31st, the picture that emerges is humbling. The Milky Way would form around March 16th. Our solar system would not appear until September 2nd. Life on Earth would begin around September 21st. The first complex multicellular organisms would not emerge until December 5th. Dinosaurs would appear on December 25th, Christmas Day, and go extinct on December 30th. The entire recorded history of human civilization, from the invention of writing to the space age, would occupy the last 14 seconds of December 31st. Everything you have ever learned about in a history class, every empire, every revolution, every war, every work of art, every scientific discovery, happened in the last 14 seconds of the cosmic year. This is not meant to diminish human achievement, quite the opposite. The fact that a species that has existed for such a vanishingly brief moment in cosmic history has managed to unravel the laws of physics, detect gravitational waves from colliding black holes, photograph the shadow of a supermassive black hole, and land spacecraft on other worlds is nothing short of extraordinary. We are the universe becoming aware of itself. We are matter that has organized itself to the point where it can contemplate its own origins and its own fate. Let us now discuss one more frontier of space science, the search for the origins of life itself. One of the most remarkable discoveries of recent decades is that the building blocks of life are not unique to Earth. Amino acids, the molecules that form proteins, have been found in meteorites, in interstellar gas clouds, and in the tails of comets. Sugars, nucleobases, and other organic compounds have been detected in space. The chemistry of life appears to be woven into the fabric of the cosmos. This has led some scientists to embrace the hypothesis of panspermia, the idea that life, or at least its precursor molecules, may have originated in space and been delivered to Earth by comets, meteorites, or interplanetary dust. In this view, Earth was not the cradle of life, but the recipient of cosmic seeds that found fertile ground on our warm, wet, young planet. Panspermia does not solve the question of how life began. It merely pushes it back in time and outward in space, but it suggests that life may be far more widespread in the universe than we currently know. The question of abiogenesis, how non-living chemistry gave rise to the first living cell, remains one of the deepest unsolved problems in science. We know that life on Earth began at least 3.5 billion years ago, and possibly as early as 4 billion years ago, remarkably soon after the planet had cooled enough for liquid water to exist. This rapid emergence of life suggests either that the origin of life is relatively easy given the right conditions, or that Earth was extraordinarily lucky. If the former is true, life may be common throughout the universe. If the latter is true, we may be alone. Experiments have shown that many of the basic building blocks of life can form spontaneously under conditions that may have existed on the early Earth. Lightning strikes in a reducing atmosphere, hydrothermal vents on the ocean floor, or ultraviolet radiation acting on simple molecules. But the gap between simple organic molecules and a self-replicating, metabolizing cell is vast, and no experiment has yet bridged that gap. The origin of life remains a mystery, but it is a mystery that scientists are attacking from multiple angles, using chemistry, biology, geology, and astronomy. Let us also reflect on something that is rarely discussed but deeply important: the fragility of our existence. Earth is a remarkably hospitable world, but it exists in a universe that is overwhelmingly hostile to life. The vacuum of space is lethal. The radiation that permeates the cosmos is lethal. The temperatures found on most celestial bodies, from the frozen wastes of Pluto to the searing surface of Venus, are lethal. Earth is protected by a magnetic field that deflects the worst of the solar wind and cosmic radiation, by an atmosphere that shields us from meteorites and ultraviolet light, and by a stable, long-lived star that provides just the right amount of energy. Remove any one of these protections, and life as we know it would be impossible. We are, in a very real sense, living on a tiny island of habitability in an ocean of hostility. The fact that such an island exists at all, that the conditions for life emerged from the chaos of the Big Bang, the formation of galaxies, the birth and death of stars, and the assembly of a rocky planet at just the right distance from a well-behaved star, is either the most remarkable coincidence in the history of the cosmos or the inevitable consequence of a universe that is far larger and more varied than we can currently observe. As we bring this journey to a close, let us consider what lies ahead, not just for space science, but for humanity's place in the universe. We stand at a pivotal moment in history. For the first time, we have the technology to detect signs of life on other worlds, the capability to deflect asteroids that threaten our planet, and the ambition to send humans to Mars and beyond. The questions we are asking today: are we alone? What is the universe made of? How did it begin and how will it end? are the same questions that our ancestors asked when they first looked up at the night sky. But for the first time, we have the tools to begin answering them. The next few decades will likely bring discoveries that fundamentally reshape our understanding of the cosmos. The James Webb Space Telescope may detect biosignatures in the atmosphere of an exoplanet, providing the first evidence of life beyond Earth. Gravitational wave observatories may detect signals from the earliest moments of the universe, opening a new window onto the Big Bang itself. Particle accelerators may reveal new particles or forces that explain dark matter, and theoretical physicists may finally develop a unified theory that reconciles quantum mechanics and general relativity, revealing the deepest structure of reality. Or the universe may surprise us in ways we cannot currently imagine. That is, after all, what it has always done. Space exploration is often justified in terms of practical benefits, technological spin-offs, economic growth, national prestige, and the development of capabilities for planetary defense. These are all valid and important reasons, but the deepest motivation for exploring space is something more fundamental. It is the same impulse that drove our ancestors to cross oceans, to climb mountains, and to map uncharted territories. It is the irrepressible human desire to know, to understand, to push beyond the boundaries of the known and into the realm of the unknown. The universe is vast beyond imagination. It is ancient beyond comprehension. It is beautiful beyond description. And it is ours to explore, not because it is easy, but because the act of exploration is what gives our brief existence meaning. Every photon of starlight that reaches your eye has traveled across the cosmos for years, decades, centuries, or millennia to reach you. Every element in your body was forged in the heart of a star. Every breath you take contains atoms that have been cycling through the cosmos for billions of years, passing through clouds of interstellar gas, through the cores of dead stars, through the atmospheres of alien worlds. You are not merely an observer of the universe, you are a part of it. You are the cosmos experiencing itself. Look up tonight, look at the stars. They are not just points of light, they are suns, many with their own planets, their own stories, their own mysteries. Some of the light you see left its source before human civilization began. Some of it left before life existed on Earth. You are seeing the past, preserved in photons, delivered to you across the vast emptiness of space. And somewhere out there, perhaps orbiting one of those distant stars on a world we have not yet discovered, something might be looking back. Something might be asking the same questions we ask. Something might be wondering just as we do whether it is alone. The universe does not owe us answers, but it has given us the ability to ask the questions. And in the asking, in the searching, in the wondering, in the relentless pursuit of knowledge, we find something that transcends our smallness and our brevity. We find purpose, we find connection. We find meaning in the magnificent, terrifying, incomprehensible immensity of it all. This is the story of space. It is not finished. It will never be finished. Because as long as there are minds capable of wonder, the story will continue to unfold, one discovery at a time, one question at a time, one star at a time. The cosmos is calling, and we are listening. Thank you for joining us on this journey through the universe. The stars will be waiting whenever you are ready to look up again.